Often, we have to deal with missing values in our data. They could look like not numbers, empty strings, or outliers like -999. Sometimes they can contain useful information by themselves, like what was the reason of missing value occurring here? How to use them effectively, how to engineer new features from them, will be the topic for this video. So, what kind of information missing values might contain? How can they look like? Let's take a look at missing values in the Springfield competition. This is a matrix of samples and features. People manually reviewed each feature and found missing values for each column. These values could be not a number, empty string, -1, 99, and so on. For example, how can they find out that -1 can be the missing value? They could plot histogram and see that this variable has uniform distribution between 0 and 1, and that it has small peak of -1 values. So, if there are no not numbers there, we can assume that they were replaced by -1. Or, the feature distribution plot can look like the second figure. Note that x-axis has log scale. In this case, not numbers probably were filled by feature's mean value. You can easily generalize this logic to apply it to other cases. Okay, on this example we just learned this. Missing values can be hidden from us, and by hidden I mean replaced by some other value beside not a number. Great, let's talk about missing value imputation. The most often examples are: first, replacing not a number with some value outside feature value range; second, replacing not a number with mean or median; and third, trying to reconstruct value somehow. First method is useful in a way that it gives trees possibility to take missing value into separate category. The downside of this is that performance of linear models and neural networks can suffer. Second method is usually beneficial for simple linear models and neural networks, but again, for trees it can be harder to select objects which had missing values in the first place. Let's skip the feature value reconstruction for now and turn to feature generation for a moment. The concern we just have discussed can be addressed by adding new feature is now indicating which rows had missing values for this feature. This can solve problems with trees and neural networks while imputing mean or median, but the downside of this is that we will double number of columns in the dataset. Now, back to missing values imputation methods. The third one, and the last we will discuss here, is to reconstruct feature value if possible. One example of such possibility is having missing values in time series. For example, we could have everyday temperature for a month, but several values in the middle of month are missing. Well, of course, we can approximate them using nearby observations. But obviously, this kind of opportunity is rarely the case. In most typical scenario, rows of our dataset are independent and we usually will not find any proper logic to reconstruct them. Great! To this moment we already learned that we can construct new feature is now indicating which rows contains not numbers. What are other important moments about feature generation we should know? Well, there is one general concern about generating new feature from one with missing values. That is, if we do this, we should be very careful with replacing missing value before feature generation. To illustrate this, let's imagine we have a year-long dataset with two features, daytime feature and temperature, which had missing values. We can see all of this on the figure. Now, we fill missing values with some value, for example with median. If we have data over the whole year, median probably will be near 0. So, it should look like that. Now we want to add feature like difference between temperature today and yesterday. Let's do this. As we can see, near the missing values, this difference usually will be abnormally huge, and this can be misleading our model. But hey, we already know that we can approximate missing values in time series by interpolating between nearby points. Great. But unfortunately, we usually don't have enough time to be so careful here. And more importantly, these problems can occur in cases when we can't come up with such specific solution. Let's overview another example of missing value imputation, which will be substantially discussed later in advanced feature engineering topic. Here we have a dataset with independent rows, and we want to encode the categorical feature with the numeric feature. To achieve that, we calculate mean value of numeric feature for every category and replace categories with these mean values. What happens if we fill not the numbers in the numeric feature with some value outside of feature range, like -999? As we can see, all values will be driven closer to -999, and the more the rows corresponding to particular category will have missing values, the closer mean value will be to -999. The same is true if we fill missing values with mean or median of the feature. This kind of missing values imputation definitely can screw up the feature we are constructing. The way to handle this particular case is to simply ignore missing values while calculating means for each category. Again, let me repeat the idea of these two examples. You should be very careful with early non-imputation if you want to generate new features. There is one more interesting thing about missing values. XGBoost can handle not the numbers, and sometimes using this approach can change score drastically. Besides common approaches we have discussed, sometimes we can treat outliers as missing values. For example, if we have some music classification task with songs which are thought to be composed even before ancient Rome or maybe after year 2025, we can try to treat these outliers as missing values. If you have categorical features, sometimes it can be beneficial to change to missing values all categories which present in the test data, but do not present in the train data. The intuition for doing so appeals to the fact that a model which didn't have that category in the train data will eventually treat it randomly. Here, unsupervised encodings of categorical features can be of help. As we already discussed in our course, we can change categories to its frequencies, and thus treat categories we never seen before based on their frequency. Let's walk through the example on the slide. Values you see from the categorical feature do not appear in the train. Let's generate new feature indicating number of value occurrences in the data. We will name this feature categorical encoded. Value A has 6 occurrences in both train and test, and thus value of this new feature related to A will be equal to 6. The same works for values B, D or C. But now, new features values related to D and C are equal to each other, and if there is some dependency between target and number of occurrences for each category, our model will be able to successfully utilize that. To conclude this video, let's overview main points we have discussed. The choice of method to fill not numbers depends on the situation. Sometimes you can reconstruct missing values, but usually it is easier to replace them with value outside feature range, like -999, or to replace them with mean or median. Also, missing values already can be replaced by something by organizers. In this case, if you want to know exact rows which had missing values, you can investigate this by plotting histograms. More, the model can improve its result using binary feature isNow, which indicates what rows had missing values. In general, avoid replacing missing values before feature generation, because it can decrease usefulness of the features. And in the end, XGBoost can handle not the numbers directly, which sometimes can change the score for the better. Using knowledge you have derived from our discussion, now you should be able to identify missing values, describe main methods to handle them, and apply this knowledge to gain an edge in your next competition. Try these methods in different scenarios, and for sure, you will succeed.